Good morning. So today we will be discussing about strips. Strips is a language which was developed for Shaky Robot, and its full form is Stanford Research Institute Problem Solver. ST stands for Stanford, R stands for Research, I stands for Institute, P stands for Problem, and S stands for Solver. Now a plan, let's define what we mean by a plan, and then let's see the components of what of a planning system. A plan is assumed to be a sequence of actions, and each action has its own set of preconditions that need to be satisfied before we perform that particular action. And the side effects of a particular action can be either positive or negative. For example, let's say I am at home drinking, intending to drink tea. That means I am at home and I want to drink tea. The initial state is I am at home, but I do not have tea. Now, in order to get the tea, I need to go to a tea seller. Okay, I need to go to a tea seller. Now, when I go to a tea seller, in that case, the action is go. But what is the side effect of the action? I am no more at home. I am at the tea seller's place, right? So, no more at home is a negative effect of performing a particular action, and the positive effect of this action is what? I am at the tea seller. Fine. Now, for any planning system, the domain description is important. Along with that, the action specification, which has a set of preconditions, and the goal description is required. Now, there are two ways of planning a particular scenario in order to achieve from the start state to the goal state. Now, what do we do in case of forward state planning, space planning is, over here we start from the start state and then find out all possible solutions in order to reach the goal state. Okay, start from the start state S in any, be it any domain, and then keep on performing actions in order to acquire new state S dash, and then progress in such a way that you are able to reach the goal state. The actions have to be applicable in this case. Now, any action that we take should be applicable to this particular case. Okay. The disadvantage of such an planning is that there is a huge branching factor. There could be multiple possible solutions and again multiple paths within each new state. Advantage of this problem, advantage of this algorithm or planning is that it is sound. Now, the other counterpart of forward state space planning is the backward state space planning. So, what happens in this case is we start from the goal state, take a backward path in order to reach the start state. Okay, we move back in order to reach the start state. Now, from the goal state, I'll go back to check the sub goals, and then from the sub goals again the sub goals for that particular sub goal. Now we keep on backtracking to check whether we are able to reach the start state. Right? Now let's go through this. Now, in case of this planning, it behaves in a similar fashion as that of the backward state space search, wherein we move from the goal state G towards the sub goal G dash. This is like finding previous action that needs to be done to achieve a particular goal. Now, this process is also called as regression, that is moving back to the previous goal or the sub goal. Now, these sub goals have to be checked for consistency as well. Now, the actions of course have to be relevant in this case as well. Now, what is the disadvantage of this particular BSSP? Now, over here in such a backward state space planning, it is not a sound algorithm. Sometimes inconsistencies can be found. Now, what is that inconsistency? When you're moving backwards, you may get lost. And also, the advantage of this is the branching factor is very small as that of the forward state space planning. So now since we have understood the advantage and disadvantage of both the planning methods, it is better to have an efficient planning system which combines the good features of both FSSP and BSSP, which gives rise to goal stack planning. Let's see what we are doing in this goal stack planning or the block world problem. Now, having understood that planning is a process which involves several steps of problem solving before executing any of them. Now, planning consists of choosing the best rule out of multiple rules and apply this rule on a problem to get into a new state. Right? Once we get into this new state, we need to detect if we have reached the solution, that is the goal state. If we have achieved the goal state, in that case we stop performing the application of rules. If we have reached a dead end, we need to explore new directions in order to reach the goal state. And also we need to detect when an utmost correct solution has been found. Now this is one of the most important planning algorithms which is specifically used by STRIPS. The block world seems to be the most important planning algorithm. The stack is used in the algorithm to hold the action and to satisfy a particular goal. A knowledge base is used to hold the current state actions. The goal stack is similar to the node in the search tree. There are branches created which helps us to choose a particular action. Now over here, in order to choose a rule, consider the goal state and compare it with the initial state. Then identify the relevant rules that have to be applied. Now over here we are performing the BSSP. Now the important steps in this particular algorithm are: start by pushing the original goal onto the stack. So we should be aware of the goal state that we need to achieve. Repeat this until the stack becomes empty. If the stack top is the compound goal, then push its unsatisfied sub-goals on the stack. If the stack is an unsatisfied single goal, then replace it by action. Fine. And then push the action's precondition onto the stack to satisfy the condition. Now if the top of the stack is an action, pop it out of the stack, execute it, and then change the knowledge base by the effects of the action. If stack top is a satisfied goal, then pop it from the stack. Now these are the 4 important steps that we will be performing iteratively. Now let's try to understand the block world problem or the goal stack problem with the help of this particular illustration. Over here we have an initial state. Now let's assume this is the table over which the blocks are placed. Now in the initial state, over the block A we have block C, and over the block B we have block D. Totally there are 4 blocks A, B, C and D. And the final state that we wish to achieve is A and B is over A. Okay, A and B. Now this is the state which we want to achieve, and we call this final state as the goal state. Now there are 4 actions that we need to perform in order to achieve the goal state from the start state. Now the first action that we need to perform is stack x over y. Fine. Now over here the precondition that needs to be satisfied in order to complete this action or execute this action is the robot arm should be holding an x, and also the block y should be clear. That means no other block should be placed on this particular y block. Fine. Now the second action is unstack x and y. Now you have to unstack x from y. Now what do we do? How do we achieve this action? Now the precondition here is check if the arm is empty. If the robot's arm is empty, and if x is over y, and check if x is clear. Then moving further, we have an action called as pickup. Pick up a particular block. Over here we are picking up x, and in order to pick up x, in order to perform this action, the precondition is check if the arm is empty, if X is on the table and if there is nothing over the block X. Okay. Now, if all these three preconditions are satisfied, the pickup of this particular block can be performed by the robotic arm. Now, what is the last action that we need in order to achieve the goal state? One, it is put down action. Put down a particular block on the table. Now, the precondition is, in order to put a particular block, the robot arm should be holding that particular block. Now, to put the block X, put down the block X, the robot should be holding X. Now, getting back to our problem, now over here we can specify the goal state as on A, I want the block B. Okay, on A, I want the block B. This is the final state that has to be achieved. And how do I achieve this? From this initial state. Is B free? There is something over B. D is over B and C is over A. Now what do we do initially? I need to work by clearing C from A, and also I need to clear D from B, which is put on B, and then place this B over A, right? So what is the first action? I need to stack B over A. Now we are backtracking, we are going in the reverse direction, regression, right? So I want to stack B over A. Okay, what is the precondition that is required in order to stack it? Hold B, the robotic arm should hold B and check if the block A has nothing over it. That is, if block A is clear. Now, when you check the initial state, you can see that is the block A clear? Is it an yes or a no? It is a no. It is not clear. So what is the action that we need to perform? We need to unstack this C and then clear this A. How do we do that? So over here, first unstack C, which is present over A, and the precondition to perform this action is check if the robot's arm is empty. And then if C is on A, clear, and then check the condition, clear A. Now is A clear? No. And is C on A? Yes, C is on A. So what we can do is we can pick, the robotic arm can pick C, which is present on A. Now we can see that after I perform these actions, I can after I perform these preconditions, I can perform this action of unstacking C from A. Now once I perform this unstacking of block C, which is present over block A, the robotic arm is having the block C and A is clear. Now we can see that this condition is satisfied once I perform the unstack operation, right? Now over here, clear A, it is an S. Now moving on to the other precondition to reach the final state, that is hold B. Is the robotic arm holding B? No. So what do we need to do? We need to pick up B, and the precondition to pick up B is the arm should be empty and B should be on the table and there should be no other block over B. Okay, these are the three preconditions that needs to be satisfied in order to perform the action pick up B, which is in turn helping us to hold B, helping the robotic arm to hold B. Now let's check the preconditions. Is B clear? No, there is D over it, right? There is B is not clear, there is D over it. And what do I need to do in order to make B clear? I need to unstack D, which is present over B. Now we have seen how to unstack. First check if the arm is empty and also whether D is over B, and then clear D. Now is D clear? Yes. So what is the next thing I can do? I can check if D is over B. This condition is also true. And is the arm empty? No. Arm is having what? Arm is having a C over it. Okay. So what do I need to do? I need to put down the C somewhere on the table and then pick up this particular D. So over here we can see at the bottom there is an action which needs to be performed, which is called as put down C, and the precondition is the robot should be holding C. Yes, the robot is holding C. This condition is satisfied. So I can perform the action put down C. Now how can I put it down? I will place C somewhere on the table and then I can perform what? The arm is empty. So I can unstack D, come back to this condition. Is the arm empty after I put down this particular C by performing this action? Yes, the arm is empty. So I can perform the action of unstacking because all the three preconditions are satisfied now. Now unstack B. So D will go to the robot's arm and B will get clear. Now B is moved to the robot's arm and B is clear. Now this was required in order to perform the action pick up B. Now let's get back. Now once I complete the unstack operation, now I can say that B is now clear. Fine. Now check if B is on the table. Yes, it's on the table. But is the arm empty? No. Arm of the robot is having a D. So I need to put down this D and then I can pick up this B. Now in order to put down D, I need to check whether this condition is true. That is the robot arm holding D? Is the robot arm holding D in this scenario? Yes, it is holding D. Now I have placed D over here, and then once I place the D, what can I do? The robot has put down D. That means this action is completed. Now what will I do? I need to check if the arm is empty now. Is the arm empty? Yes, the arm has got empty, so I am able to pick up B. So I will pick up B. The robot arm has picked up B. So the robot arm is holding B and there is nothing over A. Now I can stack B over A. I can complete this action in order to achieve the final state. So this is one simple example as to how strips can be used to achieve the planning in case of the block world problem or the stack problem, goal stack problem.